All right, we're going to take a look at lesson 2.3. What are we doing today? We are going to be rewriting exponential functions. So today is a lot heavier dosage of exponentials and only exponentials. That's what we're looking at today. All right, so exponential functions. Remember, as last class I told you, let me just use this equation. The most frequent equation you're going to see is y equals a dot b to the power of x. That's typically what we would say is an exponential function. And I want to remind you that this a right here is referred to as the initial value. That is the initial value, whereas b is called or referred to as the base. The reason we call it exponential is because the x, the variable, the independent variable, is located in the exponent. That's why we call it exponential. It's because the variable is located in the exponent. Okay, so just a reminder, the equation we're looking on, this would model what in sequences? What type of sequence? Geometric. This is similar to, it's similar, if you remember, to the geometric. Gn equals gk times r raised to the power of n minus k. It's similar to that equation we had before. This, when I gave you this one, this is this gk does not have to be the initial. And so today we're going to talk about how these two can correspond, even though they don't, this doesn't have the minus value, and this is the initial. How can they correspond? Well, we're going to learn about that today. So with that, let's get started. The first thing I want you to look at is, oh, here it is. An exponential function has the general form. Sorry, I forgot to put the slide on there. What is the general form? Just gave it to you.
A times b to the power of x.
A times b to the power of x, where the initial value is a. Okay, here's what you need to know. A cannot equal 0. The initial value cannot be 0. Think about it. What is 0 times anything?
0.
0. That's right. And there's one more thing about b. B cannot equal 1. Now, why would that be the case? What is 1 to the third power?
1.
What about 1 to the fourth power?
1.
What about 1 to the fifth power? Okay, it would be a line then. If anything times 1 is itself, it would be a constant line. So for that reason, a cannot be 0 because that would just give us a constant 0 slope. And if b is 1, then we have a line as well. It's just a constant, it's a constant function at whatever value a is. So those are your two rules with it to be exponential. So exponential growth is when it increases. Notice exponential growth is always increasing. I'm going to write this on there. Always increasing. Always increasing. You see how that works? Always increasing. Whereas exponential decay, what can you tell me about that? It's always decreasing. Yeah, it's a lot harder for me to write sideways, but I'm trying my best. Always decreasing. So add that into your notes as you go along. Always decreasing. Now, just because it's always decreasing doesn't mean it goes down to negative infinity. It will not go down to negative infinity. These have horizontal asymptotes. If you want to add those, if you have your ID, you can add a horizontal asymptote to your packet. I'd recommend that. That's the horizontal asymptote, y equals 0. That means, remember when we wrote limits? A limit doesn't tell you where the graph is. A limit tells you, for example, this limit, if I wrote it on this function here, this decay function, the limit of, I'm just going to write in decay, the limit of decay. The limit of decay as x goes to infinity here would equal, okay, so if I ask you, does this graph rise? Does it fall? Or does it get really flat? What appears to happen on this exponential? It gets really flat. Now, what value is it approaching when it gets flat? 0. So a limit on a decay would be approaching 0. Whereas on the growth, the limit would be not as x increases without bound, meaning going to positive infinity. It would be when x decreases without bound, as x goes to the left. What happens to this graph as we go to the left? Does it fall? Does it rise? Does it get flat? It gets flat and it's approaching the value 0. Now, to be specific, I heard it falls to 0. I actually want to say it falls to 0. falls indicates it's going to negative infinity. I would say it approaches 0. It is true that it's decreasing to 0, but that's I wouldn't say it falls to 0, just to be clear. All right. Oh, one more thing. To be growth, typically we think of the base. Now, negative a would throw this off, but for the most part, if the base is bigger than 1, we typically think of this as growth. Again, you can transform it with a negative out front, and sure, that would change it. But without transformations, if b is greater than 1, it's growth. If b is somewhere between 0 and 1, it's decay. We don't work with a negative base for exponentials because a negative base could not be continuous. I'll say it again. A negative base would not be continuous. So it would not be an exponential function. It could be a geometric sequence, but it won't be a exponential because it's not continuous. It would be discrete. It'd be bouncing back and forth. Okay. So now growth is bigger than 1 base. Decay is less than 1. That is without a transformation. However, we sometimes have transformations. So we're going to give a little chart of all the different ways it can turn out. So let's say your base is greater than 1. Typically, what happens if your base is greater than 1? It's going to be growth. You typically think of that. That's when a is also positive. So here's what I want you to do. Come over here and draw an exponential function. So an exponential function typically, without transformations, goes through the point 0, 1. I'm going to add that right here. It has a y-intercept at 0, 1. And again, on the graph, I will add that exponential, I'll add the horizontal asymptote. So again, add that to your graph. Those are, a graph will look somewhat similar to this. And I'll add one more point. This will be helpful for you when you do your homework. At a x value of 1, it's going to be going through the point whatever the base is. So I want to put 1 comma base. So what do I mean by that? If your base is 3, if your base is 3, this point would go through 1 comma 3. If your base is 4, your b is 4, it would go to point 1 comma 4. Follow what I'm saying? So what if the base is 10? It's going to go through 1 comma 10. They always will go through without a transformation. It'll go through 0 comma 1. But then,
Isn't that supposed to be y equals 0?
say it again.
The horizontal what?
The horizontal asymptote. Oh yeah, y equals 0. Sorry. And you know what? I just realized. Sorry, I'm so used to doing this. Did I get it right in the previous slide?
Yes.
Okay. I'm so used to doing this with regulars. For y'all are pre-AP, y'all are AP. It's not going to be 0 comma 1. It's going to be 0 comma a. I forget. Y'all's difficulty is a little higher. Sorry. If y'all are regular pre-cal, I would have been 0 comma 1. But y'all are 0 comma a. Whatever your a is, that's your initial value. So there we go. Add that on there. All right. So now, sorry about that. The guy corrected now. Let's now do this one. What's happening when your base is between 0 and 1?
It's decaying.
It's decaying. Okay, so this time, draw your graph coming in this way. Like that. Once again, add that asymptote at y equals 0. Y equals 0. Okay, so and we're going to add those 2 points. Again, it's going to go through 0 comma a, and then add the point 1 comma base, which this time I'll just do b for base. So add those 2 points. All right, so growth, decay. This would be called growth. This one would be called decay. Now come over here. What happens if a is negative? So if A is negative, where will that first point be? The y-intercept. Where would that be located? If A is negative.
On 2.
So if A is negative, would it still be up? No, now where will it be?
Down.
Down. So what's going to happen this time is if you have a negative A and it's supposed to be growth, like the base is growing, but it's a negative A, you're actually going to decrease without bound like this. And so we would actually now call it exponential decay. It's kind of tricky, but we still have the same asymptote. That's y equals 0. That's still there. But now this point, since A is now negative, 0 comma A is now negative, A is less than 0, so it's down low. And this point would still be 1 comma you know what? A dot B is mathematically the accurate value here. A dot B. I'm so sorry. You know, when you do something for 10 years straight, it's hard to change it on the fly. All these should be A dot B. Again, I've done something for 10 years straight and I'm having to change it for AP. It's tricking my mind. Hey, don't worry. If you take me again next year, I'll have all this worked out, like just a year to buffer it out. So if you want to take me again next year.
I mean, you teach calculus?
No, I'm talking about pre-cal. Take this course again next year. I won't. I'll have it worked out. Promise.
No, he means like if we fail.
I'm actually just joking with you. Hey, what do we call this? Growth or decay? What's happening? It's now decay. All right, great. And last one. What if we have a base between 0 and 1 with a negative A? Well, what would happen is it's a vertical reflection here of this graph. And so our graph would now come up and over. Whoops. Like that. And so the points, and this time we're gonna get it right. All 4 points. Here we go. This would be 0 comma A. Whoops. 0 comma A. You're gonna have the point 1 comma A dot B. And you'll have the horizontal asymptote y equals 0. This would be called growth. So you might hear me talk about the 3 key features, and that's what I'm referring to here. All of these points that I put on each graph, those would be the 3 key features: the horizontal asymptote, the y-intercept, and the point at 1, which is A dot B.
Wait, so how come for the one on the top when it comes to 0 is less than B or less than 1? You have 1 comma x 1 1 and then 1 negative 1 5.
You talking about the exact location?
Yeah.
Well, it just depends on what A and B are. So it doesn't have to be specific. I mean, why is that one right there?
Yeah.
And this one's, yeah, that was just the way I drew it. It has nothing more than,
Okay.
yeah, don't overthink that. What is important that we start to get down how the values work. And again, I apologize for it, but the difference between teaching a regular pre-cal and now an AP is I gotta bring it up to College Board standards. So with that, we're gonna get started. Oh, sorry. With regular pre-cal, we have not dealt with the A. So for 10 years, I haven't been dealing with the A, hadn't had to worry about it. But with y'all, you do have to worry about the A, and that's where it's throwing me off. If you remember, I said 0, 1, I hadn't multiplied that by A, and then I said 1 comma B, I hadn't multiplied that by A. I realized, wait a minute, now that we're dealing with A, I got to multiply those by A. So sorry for that. That's why the mistake's been there. But I got corrected. We're good. Notes are good now. Ready? All right, here we go. So it says identify if the exponential function is growth or decay and justify your response. So let's look at example 1 here. When you look at this equation, would you call this exponential growth or decay? What do y'all think on this one?
Decay.
Why are you saying decay? Because what determines is both your A and your B working together. What can you tell me about A?
A is 2.
And is 2 positive or negative? So the symbol for positive is greater than 0. A is positive, and what is our B value? 0.6, which happens to be less than 1, but it's greater than 0, which by rule needs to be. And so when you look over here, if A is positive and B is less than, or it's in between 0 and 1, it has to be decay. That would be this situation right here. That's what the graph would look like. So A is positive, which means we're at the upper end of the graph. Since B is between 0 and 1, it's going to be approaching the asymptote as it goes to the right. Okay, what about this time?
This one is growth.
Why do y'all say growth?
Because B is greater than 1. Yeah.
So it's not just because of the B. You have to A and B together. What can you tell me about my A value?
It's greater than 0.
2. That means it's going to be in the upper half of the graph. The upper half of the graph, since it's greater than 0. Now tell me about my B. If B is 7/5, is it growing or decaying in the upper half? It's growing. It's moving away from the horizontal asymptote. And since that's greater than 1, it's moving away from the horizontal asymptote. Okay. Third one. What do y'all think this time?
Decay.
It is decay. How do you determine it's decay? A is 4/3. Now, what's the test on A? Is if it's positive or negative. Is that positive or negative?
Positive. So it's greater than 0.
If it's positive, that means we're in the upper end of the graph. So now I just ask, is my base going to be approaching the horizontal asymptote or moving away from it? If it's 1/6, is it approaching the horizontal asymptote or moving away from it? It's going to be approaching it because it is less than 1, but greater than 0. Okay, so that's what makes that decay. And again, you could go back to the previous chart as long as you write these in and look at them later, and you'll see that this follows all of them. Okay, what about number 4?
Okay. I'd say growth. Growth, yeah, growth.
All right, Chris, talk me through why you say growth.
Is greater than 1 and value that always.
So that's the A is 0.2. What's the test on A? You want to know if it's positive or negative. Is A positive or negative?
Positive.
So that's the upper end of the graph. Since B is greater than 1, it's going to be moving away from the horizontal asymptote, meaning that's going to be growing. Okay, now let's move on down below it here. It says examine the function 3 times 2 to the power of x. What are we doing to the initial value 3 when the input value x is 5? Now I want to make sure you understand how exponential functions work. So 3 times 2 to the input value 5, that's f of 5 here. That's the same thing as saying 3 times 2 times 2 times 2 times 2 times 2. How many 2's are there? Is that a surprise to you?
No.
No, that's what 2 to the 5th means. Okay. So would this be growth or decay?
Growth.
Growth. Growth since. Why?
Because your A is positive and your B is greater than 1.
I forgot to put B equals 2, which is greater than 1. And it makes sense when you look at it this way. Why would that be growing? Because if I'm multiplying by numbers bigger than 1, what's always happening if you're multiplying by a number bigger than 1? Getting bigger. And is there any negative in there whatsoever? Do you see any negative anywhere? That's why it's going to be just getting more and more positive. That's why it's growing. Okay, so now the following values are output values of an exponential function. Write the function along with the input value that represents the output value. Okay, 4 times 4 times 4 times 1.5. Question for you. What do you think is the base?
Base
That's
is
has the power. Base
4.
has the power.
4.
Why would you say 4?
Because 4 is 1 that's repeating 3 times.
4 is repeating 3 times. Okay, so what would that make 1.5?
They're making A the initial value.
All right, so 1.5 times,
4 to the power.
and I'm going to put this in parentheses, times 4 to the, and I'm going to, for this, since it says f of x, I'm going to leave it x And this says where x equals, now what does x actually equal right here? Where x equals 3, perfect. Okay, and one more of these. Examine here. What do you think is the base this time?
0.8.
Why do you think 0.8?
Because it was twice.
It's the repeating. So what's 3.2?
The A.
The initial. That's the A. Again, since this says f of x, I'm going to leave the variable as an x there. But there it says where x equals. Now, what does x actually equal in this one? 2. Good. So there's a lot on that chart, but that's just a little way to kind of walk you through a lot of the basics of this. All right, so now let's kind of, I'm going to say switch gears, and let's talk about how we can start modifying or transforming these equations. So there are some properties you need to be aware of with exponentials, okay? So here, this is just a chart for you. I want to make sure you're totally familiar with this. So b to the power of n, b to the power of n. It kind of looks weird if you just look at the math symbols. So let's translate by plugging in some numbers. Instead of saying b to the power of n times b to the power of m times b to the power of n, let's look at what is x to the fifth times x to the third. So that's x times x times x times x times x.
X8.
Times x times x times x.
X8.
That would be x to the 8th power. What did you do there? Let's see for the left. It'll go back around. No, it's still not working. You would add powers together, just like it says with the power property to do. Not the power property, I'm sorry. Product property. This would be x to the 8th power. Okay, what about here? 2 to the power of x times 2 to the power of 3. Well, it's the same base, so I can combine them. It would be x plus 3. Do we know what x is? No, so we have to leave it as x plus 3. So what about a power raised to another power? B to the power of m raised to the power of n. That says to, and this makes sense because if you have x to the 5th times 3, excuse me, x to the 5th raised to the power of 3, what that means is that's the same thing as x to the 5th times x to the 5th times x to the 5th. You see how I wrote that out 3 times? And now you could use this rule. And what do you do if it's the same base, just different exponents? What do we do over here? We added them. So let me break this down. 5 plus 3, which equals x to the power of 8. Okay, so what would this equal then? X to the 15th. Very good. So 2 to the x quantity cubed would be the same thing as 2 to the x times 2 to the x times 2 to the x. And so what would you get here? Would it be x cubed?
Yes. 2 to the power of 3.
It'd be 3x. So writing it this way, you would be adding x plus x plus x. What is x plus x plus x? Is that x cubed or 3x's?
3x.
3x's. And so it'd be this way. Now that's called the power property. And finally, a negative exponent. What's the rule when you have a negative exponent? Well, you can take the reciprocal of the base. So this just flips. Now, this is not actually a fraction. I want to show you a fraction one in a second. I should have added it right here. But x to the negative third is the same thing as what is x if you wanted to make it being divided by something? What would I say it's divided by? You can take the reciprocal and say it's the same thing as 1 over x. And I'm going to put this in parentheses. Cubed. Now, why I did this is because sometimes you're going to actually have a fraction. Maybe it's 2/5. And it's important that you cube everything. This one doesn't exactly look like you're cubing everything, so I want to write it this way. Now I'll simplify 1 time. What is 1 times 1 times 1?
1.
So this would be 1, and then x times x times x?
3x.
Not 3x, but
X.
x cubed. Okay, this time, again, this 2 is not a fraction. So to make it a fraction, I'd say it's 2 divided by 1. So you take the reciprocal of the fraction, 1/2, and you raise it to the power of x. Now this I can simplify. What is 1 to the power of x? No matter what x is, what's 1 to any power? 1. Even 1 to the 0 power is still 1. You didn't know that. Anything to the 0 power is still 1. So 1 to any power is 1. That's not the case with 2. That will change. So I'm gonna leave it at 2 over x. Okay, so there's some important properties for exponents, both the product, the power, and the negative exponent. By the way, it's not on here, but there is a quotient property. A quotient property. Let me make sure it's on the next page. Nope. We should have a quotient property. Why do I not have the quotient property on there? What about the quotient property? Do y'all know what that is?
You divide x's.
Okay, so what do you think b to the power of m divided by b to the power of n would equal?
Would be
E to the power of n.
There you go. B to the power of n, m minus n. So think about it. X cubed divided by x squared. X cubed divided by x squared. What would that equal? X1, because you just subtract powers. Or if you wrote it out, you could cancel powers, simplify powers. So put the quotient property on there as well. That should be on this slide. All right. You good? Got it. Sorry. There you go. Get it quickly. All right. So now let's get into the meat of this lesson. A horizontal translation, a vertical dilation. When doing exponentials, these will appear to be exactly the same. So here it says the same exponent rules can be used when working with horizontal transformations of exponential functions. Let's think of a horizontal translation as an exponential function. Horizontal translations, that means we're shifting either left or right, is equivalent to a vertical dilation. So that's what it's saying. A horizontal translation that says shift left and right is the same thing as vertically stretching or shrinking an exponential function. So here we are, just to show you. This function is, the blue is 2 to the power of x. Here it's 2 to the power of x plus 3. Now remember, when you have a transformation on the inside with x,
x's are liar.
it's a liar. So which way does this actually get shifted? Left 3. So this graph has been shifted left 3. You see how this graph has been shifted left 3? Left 3. So if you took any point, let's just take this point. It's been shifted 1, 2, 3. The graph doesn't look that specific, but it should be shifted left 3 units. That's what should have happened all the way through. Everything shifted left 3 units. If you have any 2 points, it should be a leftward shift by 3 units. But what this is saying is if I use my properties, that happens to be equal to, this right there, happens to be equal to 2 to the power of x times 2 to the power of 3. Now, why is that the case? Because what property was this? I almost told you, but I'm gonna make you go back and look on the properties. What's the name of that one?
That is the power.
No, it's the product.
It's the product property. So I'm gonna just say PTY. The product property tells you that this is the same thing as 2 to the x times 2 to the power 3. Now, what is 2 to the power 3?
8.
And thus we get this equation here. You see how that's 8 times 2 to the power of x? And so you get the same graph. But what's different this time is now every single y value has been multiplied by 8. Any y value has been multiplied by 8. So it's a vertical dilation. A vertical. This I should have said shift. Shift. That was a shift left 3. This is a vertical dilation. That means multiply. Vertical dilation by factor 8. Every y value got multiplied by 8. That's what happened this time. And it produces the same graph. Because, again, those properties are equal to one another. So the meat of this lesson is going to be playing around with exponential functions to make them represent different values. All right. So on the first one, determine the horizontal translation / vertical dilation of each of the following exponential forms. Okay, so starting with this one, I have a transformation here. I have an x plus 2. That's the transformation. The 4 is the base, not a transformation. The plus 2 is a transformation. That is with the x. That is inside the power with the x. So what type of transformation is it? When you go to your x values and you add 2. It is a horizontal what? That is a horizontal translation. Now, question for you. Do your x transformations, are they liars or truth tellers? So horizontal translation. So it doesn't actually go to positive 2, it goes to negative 2. Which direction is negative 2 on the x-axis? Horizontal means x. It goes left 2. Now that's what that first transformation is. Now what I want to do is also write this in a corresponding form. How else could we write this equation? We could write this equation as
4x times 4 to the power 2.
4x times 4 to the power 2, which is the same thing as
4x times 16.
I'm going to put the 4 squared first. What is 4 squared?
16.
Which is the same thing as 16 times
4
4 to the power of x. Now it's not a horizontal translation anymore.
vertical dilation.
Now we'd say that is a vertical dilation. A vertical dilation. That means I'm multiplying the y's. I forgot the a. Dilation. There we go. Vertical. No. I just need to look right how to spell it right there. There we go. Dilation. Vertical dilation by factor, which means every y value, if you had a table, every y value would get multiplied by 16 from the parent function, which the parent function here is 4 to the power of x. So we don't forget, would this be called a growth or decay function? If a is 16 and b is 4, that would be growth. Good. Okay, 2 to the power of 3x. Now I'm going to start here and let's describe what's happening. You're multiplying by 3. The x is getting multiplied by 3. So is that horizontal or vertical? If you're multiplying x's, which one's x? Is that a horizontal or vertical if it's x? Okay, so we're going to start with horizontal. It's horizontal. Now, if you're multiplying, is it a translation?
No, it's dilation.
It's a dilation. Horizontal dilation. I can't spell. Dilation. There we go. Horizontal dilation by factor. Would it be 3?
Yes.
No.
2. Oh,
Do I actually multiply by 3?
No.
What do you do instead?
It's by factor of 1/3.
1/3, because I'm dividing by 3. So if I divide by 3, what's the placeholder for the 1? That's right. You multiply by 1, divide by 3, by factor 1/3. That's a horizontal dilation by factor 3. Now let's use some properties here. This is the same thing as what do we do if it's 3x? Go to your properties.
It's a 2x to the power of 3.
All right, it's the same thing as 2 to the power of 3 raised to the power of x. Is that correct? I should have been writing the properties here. What was the name of this property? This was the product property. Okay, are we using the product property this time? No, which property did we just use right there? This one's the power property. Okay, now this I could simplify and say, what is 2 cubed? 8. So this is the same thing as 8 to the power of x. So on this one, that has no transformations. What I have done is change my base. That's just a new base, but it's not a new transformation. New base without a transformation. I'm going to say that again. There's no transformation here. It's just a new base without a transformation. So my base over here was 2. Now what's my base? 8. It'd be the same graph though. Same exact graph. Can I move on?
Yes.
Got it? All right, let's try another set of properties here. I have 9 raised to the power of x divided by 2. 9 raised to the power of x divided by 2. Okay, so tell me first off, what's the transformation that's occurring right now?
Here, it's a horizontal dilation by.
It's a horizontal because it's with x. That's true, horizontal. If you add, if you add or subtract, it's a translation. If you multiply, divide, dilation. If it's a negative, it's a reflection. What am I doing here?
You're dilating by a factor of 2.
Now, why do we say by factor 2? Doesn't it look like divide by 2? But x's are liars or truth tellers? Liars. So you're actually not gonna divide by 2. What you would do is multiply by 2. Okay, so now let's break this down. What property could I use here?
I didn't see it.
Okay, so 9 to the power of x over 2. How could I rewrite that? I could rewrite it like this.
9.
That is the same thing as
9 to the power of 0.500.
you can think of it as that, or even as a fraction. I'm just going to write it this way: 0.9 times x. Is everybody cool there?
Yeah.
Now, what property do I have when I have a power multiplying with another power? So look closely at the powers, at the properties. Which one has a power multiplying another power? That is power property. So using the power property. So using the power property, when you have a power multiplying times another power, you can rewrite that as separating the powers out. Am I right or wrong saying this? Raised to another power. Is that correct or incorrect to say it that way? Is that following the rule?
Yes.
Okay, now can I simplify 9 to the 1/2?
Yes.
Yes, I can. Now, what is 9 to the 1/2? 3. And that becomes a 3, and this is 3 to the power of x. Now, this answer is what I was expecting, because here, do I have any transformation? No. I have a new base with no transformation, which is what I was expecting originally, because this is models part B. Remember on part B, let's go back. When I did part B a moment ago, we had a horizontal dilation, and what was the result of a horizontal dilation? A new base without a transformation. So when I did this one a moment ago, I saw horizontal dilation. I was expecting to get a new base with no transformation, but that's not where we ended up. So that's how I knew something's off. And I plugged in the number 1 and realized, oh man, we're way off. Okay, so let's try it one more time. Now let's be specific here. I have 5 raised to a power of x minus 1. I want you to go look at your rules. We have a power with a subtraction. Which rule has a power with a subtraction? This, it's not power. This is the quotient property. This one's going to be the quotient property. Oh, before I move on, what type of transformation is a subtraction of x?
Horizontal translation, right 1.
Okay, so this is not a dilation. This one's now a
Translate.
translation. Now, x is liars or true tellers?
Liars.
Liars. So instead of minusing 1, it adds 1. On the x-axis, if you add 1, which direction we go, Anthony? On the x-axis, if you add 1, which way we go? You sure? Which one? X-axis, add 1. Which direction you going? If you add 1, you're going this way. If you add 1, you're going this way. You go up. X-axis goes this way. Which way is positive 1?
Right.
Put that stupid phone up. Which way we go? Come on, someone call it out. Which way we going if you're add 1 on x-axis? Right 1. Horizontal translation, right 1. I know some people said it, but there's still a lot of question marks around their heads. So you're not thinking about it. Okay, so now let's apply the quotient property. When you have a power subtracting, that's the same thing as doing what?
Dividing.
Dividing. So if I'm subtracting here, what that means is I have 5 to the power of x. Instead of -1, I'm dividing by 5 to the power of 1. What is 5 to the first? So this is 5 to the x divided by 5. I could rewrite this
As
with an
Wait, wouldn't that just be new base with?
I'm gonna write this as 1/5. So I'm gonna take this 1/5 times 5 to the power of x. And so to finish this off, does this have a transformation? Transformation.
How do you get 1/5? Wouldn't you
What?
say 1 to the x?
1 to the x. No, I wouldn't say 1 to the x. You can't cancel those 5s. That's breaking PEMDAS. PEMDAS.
Oh, because the 5 on top has a.
What you'd be doing is you'd be dividing before you apply the exponent. You can't do that.
Oh, okay.
Okay. So that's why I'm breaking this down. I'm making a be 1/5. So what is this at right here? Transformation. In terms of transformation, is it a vertical or horizontal? This is vertical, and I'm multiplying. So does that make it a translation or dilation? Dilation by factor. What are we multiplying those y's by? 1/5 because it's a truth teller. Now, check it out. We're going to plug in numbers because I lost all trust in this class.
Can I go to the?
You lost all trust.
What is 1? If you plug in a 1, what is 1 minus 1? 0. What's 5 to the 0 power?
1.
1. Anything to the 0 power is 1. So if you plug in a 1, you should get 1. Let's plug in a 1 here.
How does
What's 5 to the first? 5. What's 1/5 times 5? 1. Did it work?
Yeah.
Yes, it works.
How does anything to the power of 0 equal 1?
Quotient property. Easy. Quotient property. So think in terms of quotient property. What if you had 10 divided by 10? What's that equal to?
1.
Okay, let's apply quotient property. That's a power 1, power 1. You could say that's the same thing as 10 to the power of 1 minus 1. Well, what is 1 minus 1?
0.
Anything to the power of 0 is going to be 1 because of the quotient property. So just roll it through. It doesn't matter what you do. X divided by x. Well, we could cancel those, so we'd say the answer is 1. But why is it quotient property? That's saying x to the first divided by x to the first, which is the same thing as
X to the power of 0.
x to the first minus 1, which is equal to x to the 0. Anything to the power of 0 is 1. Quotient property. That's why. All right. Let's move on to example 2. What do you say? Example 2 here. Let f of x equal 3 to the power of x. Let g of x be the transformation of f for each problem. Name the transformation. What in the world? We got to name transformations. What transformation do you see this time?
You see a dilation.
Wait, horizontal or vertical?
Vertical.
Why vertical?
Because it's on the outside.
It's not with the x. That's vertical. If you multiply it as a dilation
By 9.
by factor 9. If y'all wanted to, we could do some properties. Y'all want to do the properties backwards just to get more practice there? Would that help concrete some stuff since all the mistakes, or would it hurt you? Let's break down 9. What is 9 in terms of a base of 3? What is 9 in terms of a base of 3? 9 is the same thing as 3 to what power? 3 squared. This is 3 squared times 3 to the power of x. What do you do when you have the same base being multiplied? What do you do with the powers?
Combine.
You add them. This is 3 to the power of x plus 2. There you go. Now, would it be a vertical dilation?
Yes.
No. Yes, it's horizontal. It's with x.
That too.
And it's a translation. Good. Translation. If Chris is right, he's got this down now. If I add 2, am I actually adding to the x's?
No.
No. If it says plus 2 with the x's, what do you do instead? Subtract. So it's translation left
Left 2.
2 units. Very good. By the way, when y'all see by factor, that means multiply. All right, this time.
I said by power.
I want to rewrite this. Since y'all complained at me a second ago, I want to rewrite this. You could rewrite this as, I want to put 1 times right there. How could I rewrite this equation? 1 over 27. You got it. There you go. So what's happening this time?
Vertical dilation.
Y vertical.
Because it's.
It's not part of the X, it's part of the Y's. Y dilation. Multiplying, dividing is always dilation. What's our factor that we're multiplying by? 1 over 27. That means I'm multiplying, that means I'm dividing the Y's by 27. If I wanted to rewrite this, 27 in terms of 3, how many factors of 3 does it take to get to 27? 3 times
9.
3, 3 times 9 is 27, but how many factors of 3? 3 times 3 times 3 times, how many 3's do we need? 3 times 3 is 9 times another 3?
27.
Okay, so here we go. That's the same thing as 1 over 3 cubed. That's blending in together. Let's try that again. 3 cubed times 3 to the power of x, which you could rewrite as 3 to the power of x over 3 cubed. This is quotient property. What happens when you have the same base, but you're dividing? This is where you subtract. This is power of x minus 3. Now, would I call this a vertical dilation?
Horizontal translation.
This is now horizontal because it's with x. Horizontal. And because you're adding or subtracting, it's now a translation. If it says to subtract 3, what do we actually do?
Go to the right of 3.
Right 3.
Can I go to the version?
Yeah. All right, let's look at part C. Oh, I lied. Let's go to example 3 here. Each of the following exponential functions has a horizontal translation. For each, write an equivalent representation that has a vertical dilation and no horizontal translation. So this time we're not going to write what they are. We're just going to write it out using our properties. What property could we use on this example here? If you have a power that's adding, go to your properties if you need to. If you have a power that's adding, that's the same thing as product. That would be the same thing as 2 to the power of x times. Okay, and what is 2 to the power of 3? 8. So you can rewrite this as 8 times 2 to the power of x. Those would be equivalent representations. Do y'all want to check it or y'all trust it? Why do you trust me? You shouldn't.
Excuse me.
Well, we're the
It's
whole
Princess
got through.
Says who? All right, this time, what do you got this time? You have a base raised to a power, and then inside that power, it's subtracting. What do you do when you have a power subtracting? Quotient property. What does quotient property say? 3 over x, 3 to the power of x is now what? Over 3 squared. Okay, what is 3 squared? So that's 3 to the power of x divided by 9. And so I could rewrite that
Oh, God.
as, how can I rewrite this to make it look smoother?
1 over 9.
1 over 9 times 3 to the power of x. There you go. All right, one more time. Properties. Do I have any property? Can I multiply 4 times 3 here? It says multiply. Can I do it? According to PEMDAS, I can't because exponents come first. So let's take care of the exponents. What happens when you have exponents that are adding? Product property. What does product property mean? So you multiply like that. Whoops, it should stay consistent, so. I can simplify, what is 3 squared?
That is, nine.
9. So that's 4 times, I'm gonna take away the parentheses, times 9. Can I simplify any further?
Yes.
Of course we can. So what is 4 times 9? 36. I can't simplify those because they don't have powers. Times 3 to the power of x. There we go. All right, so it says we can also use the power property of exponents to show that every horizontal dilation of exponential function is equivalent to changing the base of an exponential function. And we've kind of done some of that already today. I've shown you change of base. I've shown you some of those. So remember, this is actually the problem that we got held up on. Mine was not x times 3. It was not 3 times x. Remember, the problem we got hung up on was x divided by 2. Do y'all remember what was our actual solution here? Go back to that problem. Where was that? Example 1C. Example 1C. It started with x over 2, which looks like a horizontal dilation. But what do we end up with having? A new base. We changed the base. That's what this one's saying here. This just came a little too late in our notes here for us. Is that you can change the base to take away a horizontal dilation. That's a horizontal dilation there. That would be dividing by c. All x is being divided by c is how that would play out. That would be a change of base. Okay, so now let's work back through these. For each of the problems, name the transformation. Okay, so here we go. We're going to simplify this. We want to get it to a power or a base of 3. You see how it says right up here? You get it to a base of 3. That's not a base of 3. How can I rewrite 9 as a base of 3? 3 squared. I could say this is 3 squared to the power of x. And that's the same thing as 3. What happens when you have a power raised to a power? Multiply. What's 2 times x? 3 to the power of 2x. So this here, did this have any transformation? Any transformation? No transformation. Here, do I have a transformation? Yes. What type of transformation? It's a horizontal. And if you multiply, it's a translation or dilation if you multiply. Dilation. Now with x's, they lie. So we're not going to say by factor 2. What are we going to say instead? Instead of multiplying by 2, I need to divide by 2. So what do I put in the numerator there if it's just
1.
There you go. Horizontal dilation by factor 1/2. Now, what in the world's happening here? Let's walk through. It's ready. Here, what is f of x in our problem?
Oh,
That's 3 to the power of x. And we need to raise that to the power of -3. Now, what can you do when you have a power raised to another power? Well, you can multiply. So that is the same thing as 3 to the power of -3x. Now, we had something earlier about negative exponents. It has to do with your base here. You can flip the base. So it becomes 1/3 to the power of 3x. Now, 1 to any power is always going to equal 1. So that's still 1. You can write it as 1 over 3 to the power of 3x. And I could leave it this way, or you could take out the 3 if you wanted to, but I'm going to leave it like this. What's happening this time? Horizontal, this is with x. Horizontal dilation. I always want to put the a first. Dilation by factor. Do I actually multiply by 3 here? it looks like I'm multiplying by 3 times x. What do I do instead? Divide by 3. Horizontal dilation by factor 1/3. And I've changed the base. So my base is now 1/3. We come to the last page. All right, we have some DOLs. Let's see what you can come up with here. See what you can work through. Oh, I have one more on there, huh? Hey, let's skip to here. I want to make sure you'll see this. So it says the kth root of b. B to the power 1k is the kth root of b. What that means is if you have a fraction power, that's the same thing as having a root. The denominator is the root. And we saw this earlier in the lesson. The same problem we broke down on, that's dividing, and this is showing you if you have a power that's not 1 over something, if it's 2/5 or whatever, how that would play out. Okay, so let's work through this and then we'll call it a wrap. So evaluate the function and the given input values. So let h of x equal this, find h of 1. So I want to plug in h of 1. That would be 2 times 5 to the power of 1/2. So what does that mean? When you're dividing by a power, that means you can take a root of it. So it's 2 times, and I'm going to do a root, and I'll put the 2 there just so you can see, times 5 to the first. So can I simplify 5 to the first?
No.
Does 5 have a good square root?
No.
So you would just say this is 2 square roots of 5. That's as simplified as it goes.
T-shirt. You have a